welcome you in the lecture series of Basics of Communication Engineering. It is 11th lecture of this series. In previous lecture, we have discussed about double sideband suppressed carrier, amplitude modulated signal generation and detection. In this lecture, I would like to discuss about single sideband suppressed carrier, SSB-SC, amplitude modulated signal generation and detection. The outline of this lecture are time domain representation of SSB-SC signal, frequency domain representation of SSB-SC signal, generation of SSB-SC signals using frequency discrimination method or filter method and phase discrimination method. Another is the detection of SSB-SC signal using coherent detection. Also, we will discuss advantages, disadvantages, and applications of SSB-SC modulation-demodulation system. And in the objective of this lecture, you will able to explain modulation and demodulation process of SSB-SC signal and advantages, disadvantages, and applications of SSB-SC system. We know that the transmission bandwidth of standard AM as well as DSB-SC modulated signal is 2 FM, that is twice the bandwidth of the message FM. So both of the system are bandwidth inefficient. In DSB-SC and standard AM, one half of the transmission bandwidth is occupied by the upper sideband and other half is occupied by the lower sideband as in frequency. But most of the important thing is that the information contained in the upper sideband is exactly identical to the carried by the lower sideband. So by transmitting both the sidebands, we are transmitting the same information twice. So there is no need to transmit both sidebands. Here we can eliminate one sideband. When only one sideband is transmitted, the modulation is referred to as single sideband modulation or single sideband suppressed carrier modulation. This SSB-SC system, which transmit a single sideband, has high power, as the power allocated for both the carriers and other sideband is utilized in transmitting in single sideband now. Let the modulating signal xt is AM cos 2 pi FMT single tone signal and carrier is AC cos 2 pi FMT. We can represent the equation of SSB-SC signal with xct. It will be AM AC by 2 cos 2 pi FC plus FMT for the upper sideband and AM AC by 2 cos 2 pi FC minus FMT for the lower sideband, as you know from the previous lecture. And the time domain display of SSB-SC signal, it is the time domain display. This is the modulating signal and this is the SSB-SC signal. This is with one amplitude and this signal is with another amplitude. Now the power calculation of SSB-SC waveform. From equation 3rd and 4th, you know xct for the upper sideband it is AM AC by 2 cos 2 pi FC plus FMT, and for the lower sideband AM AC by 2 cos 2 pi FC minus FMT. The power of SSB-SC signal is equal to the power of any sideband frequency component, that is power transmitted power will be the power of the upper sideband or power of the lower sideband. And you know the power of the upper sideband, it is AM AC by 2 whole square into 1 by 2 RL. So it will be AM square AC square by 8R, and similarly for the lower sideband it is AM square AC square by 8R. And so the power of SSB-SC signal, it is transmitted power for the upper sideband or power for the lower sideband, and it is same AM square AC square by 8R. And you have seen in the previous lecture the power required for the transmission of DSB-SC, it was AM square AC square by 4R. So it is half of the power required for the transmission of your SSB-SC signal. So now frequency domain representation of SSB-SC signal. From equation 2 we know XCT is AM AC by 2 cos 2 pi FC plus FMT for the upper sideband. So the spectrum for the upper sideband, it will be FC at a frequency FC plus FM, and we have suppressed the spectrum of the lower sideband. We are not going to transmit this. Since the SSB-SC modulated signal contains only one sideband, its bandwidth is half of the bandwidth of the DSB-SC modulation. So here bandwidth will be only this half of the DSB-SC signal. And XCF, if you will take the Fourier transform, you will get AM AC by 4 delta F plus FC plus FM and delta F minus FC minus M, and we have suppressed this. We are only having the frequency of upper sideband. So the bandwidth of SSB-SC modulation signal, it will be the half of the DSB-SC. It is 2 FM by 2. So FM hertz. Here FM is the highest frequency component of the baseband signal. So the bandwidth of SSB-SC modulated signal is equal to the frequency of the modulating signal. Now, generation of SSB-SC signals. We can generate SSB-SC signal using two methods: frequency discrimination method or filter method, and phase discrimination method. So first of all, we will discuss frequency discrimination method. This method can be used for generating the SSB-SC modulated signal if the message signal satisfy the following. The message signal should not have any lower frequency content. The audio signal has this property, that is the telephone signal will have a frequency range extending from 300 hertz to around 3.4 kilohertz, and the frequencies in this range 0 to 300 hertz are absent. The highest frequency in the spectrum of the message signal, that is FM, should be smaller than the carrier frequency. So FM should be smaller than the carrier frequency. And the block diagram of SSB-SC modulator, which operates on the principle of frequency discrimination, is in figure. Here this modulator consists of product modulator and carrier oscillator and band pass filter designed to pass the desired sidebands, upper sideband or lower sideband. At the output of the product modulator, we will get double sideband suppressed carrier signal, which contains two sidebands only, not the carrier. The bandpass filter will pass only of these sidebands and produce the single sideband modulated signal at its output. It may be lower sideband or upper sideband based on the tuning of the band pass filter. The frequency range of a band pass filter should be selected as the spectrum of the desired single sideband suppressed carrier signal. This means the band pass filter can be tuned to either upper sideband or lower sideband frequencies to get the respective SSB-SC waves having upper sideband or lower sideband. Now another is the phase discrimination method. This is the block diagram of a phase discrimination method. This system having two product modulators M1 and M2, two minus 90 degree phase shifter, one local oscillator and one summer block. The message signal XT is applied directly to the block M1 and throw a minus 90 degree phase shifter to the product modulator M2. This minus 90 degree phase shifter baseband signal XT will be a Hilbert transform x cap t. It will be AM sine 2 pi FMT and XT was AM cos 2 pi FMT. The output of the carrier oscillator is applied as it is to the modulator M1 AC cos 2 pi FCT, whereas it is passed through the minus 90 degree phase shifter and applied to the modulator M2 AC sin 2 pi FCT. The output of the product modulator M1, this is output of product modulator M1 XT AC cos 2 pi FCT, and the output of the product modulator, it will be uh, here modulator 2 is X cap T AC sin 2 pi FCT. Here the path of the product modulator M1 is known as in phase path, I path, and the path of the product modulator M2 is the quadrature path. Now we will use the summer block. If I will take the positive sign for the I path and negative sign for the Q path, then I will get my SSB-SC signal with the upper sideband. And if I will use for I and Q path the same sign, positive sign, then I will get the single sideband suppressed carrier with lower sideband. So now in mathematically we can see the output of the product modulator M1, it is XT AC cos 2 pi FCT, and here we can write it as AM AC cos 2 pi FMT cos 2 pi FCT, because XT is AM cos 2 pi FMT. So we can write it as AM AC by 2 cos 2 pi FC plus FMT plus cos 2 pi FC minus FMT, and the output of the product modulator M2, it is X cap T AC sin 2 pi FCT, or we can write it as AM AC sin 2 pi FMT sin 2 pi FCT, or we can write it as AM AC by 2 cos 2 pi FC minus FMT minus cos 2 pi FC plus FMT. By choosing the polarity of the in-phase and quadrature path of opposite sign, then we will get SSB-SC signal having upper sideband, as you have seen in the figure. So if I will take the negative sign for the quadrature path, opposite sign for these, then the output, it will be from output from the summer, it will be AM AC by 2 into cos 2 pi FC plus FMT plus cos 2 pi FC minus FMT minus AM AC by 2 cos 2 pi FC minus FMT minus cos 2 pi FC plus FMT. So this output will be AM AC cos 2 pi FC plus FMT. So by choosing opposite polarity of in phase and quadrature phase, we will get the SSB-SC signal with upper sideband. And by choosing the same polarity of in phase and quadrature path, we will get the signal with the lower sideband, just like here I am using the same polarity, and by taking summation I will get AM AC cos 2 pi FC minus FMT. This is for the lower sideband. And here, compared to the frequency discrimination method, the phase discrimination method can generate the SSB-SC at any frequency. It can also use the low audio frequency as modulating signal. In filter method, this is not possible because here we can generate only upper sideband and also lower sideband using same polarity of in phase and quadrature and opposite polarity of in phase and quadrature path. And here it is easy to switch from one sideband to other sideband, you can say. But on the other hand, the design of minus 90 degree phase shifter for modulating signal is extremely critical. So now we will discuss detection of SSB-SC signal. The SSB-SC receiver should have high reliability, excellent suppression of adjacent signal, high SNR, ability to demodulate SSB-SC. So first here we will discuss coherent detector or SSB demodulation or demodulator. The block diagram of coherent SSB-SC modulator is in figure, and you can see here the same carrier signal which is used for generating SSB-SC signal is used to detect the message signal. So this process of detecting is known as coherent or synchronous detection because we are using local. Then output of this filter is the desired message signal, and there are two cases here. Case first, let SSB-SC modulated signal is having a lower sideband. So if SSB-SC signal having lower sideband, then XCT modulated signal is AM AC by 2 cos 2 pi FC minus FMT. So it is for the lower sideband, and the output of the local oscillator, if I consider this is properly matched with the modulating signal, and it will be AC cos 2 pi FCT. So it is properly matched with the transmitting end carrier, and so the output produced by the modulator, it will be X dash T XCT into CT. It is AM AC by 2 cos 2 pi FC minus FMT into AC cos 2 pi FCT, or we can write it as AM AC square by 2 cos 2 pi FC minus FMT into cos 2 pi FCT. And we can write it as AM AC square by 4 cos 2 pi FMT plus AM AC square by 4 cos 2 pi 2 FC minus FMT, or we can write it as AC square by 2 xt plus AM AC square by 4 cos 2 pi 2 FC minus FMT. So here you can see this is the scaled version of the message signal xt, and this is scaled by AC square by 4, and it can be extracted by passing this signal x dash t through the low pass filter. So the output of the low pass filter, it will be AC square by 4 xt, or you can say xt is AM AM cos 2 pi FMT. So xt, it will be AM AC square by 4 cos 2 pi FMT. So this is the scaled version of the message signal, and it is scaled by AC square by 4. This is scaling factor. We can use the same block diagram for demodulating the SSB-SC signal having upper sideband. So just like the case if we are having upper sideband, the modulated signal is AM AC by 2 cos 2 pi FC plus FM for the upper sideband, and the output of local oscillator AC cos 2 pi FCT. Then the output of the product modulator, it will be AM AC by 2 cos 2 pi FC plus FMT AC cos 2 pi FCT, or we can write it as AM AC square by 2 cos 2 pi FC plus FMT cos 2 pi FCT, or AM AC square by 4 cos 2 pi 2 FC plus FMT plus cos 2 pi FMT, or we can write it as AM AC square by 4 cos 2 pi FMT plus AM AC square by 2 cos 2 pi 2 FC plus FMT. And the first term is the scaled version of the message signal. It can be extracted by passing this x dash t through the low pass filter, and we will get our desired baseband signal or message signal. It is AM AC square by 4 cos 2 pi FMT, and this is scaled version of message signal, and it is scaled by AC square by 4. So we can detect the SSB-SC signal, or we can say that we can extract the baseband signal from the SSB-SC signal using coherent detection. Now, advantages of SSB-SC signal: there is a reduction in the transmission bandwidth with SSB-SC, because here the bandwidth is FM, but in case of AM or DSB-SC, it is 2FM. There is power saving since the high power carrier and one sideband are not being transmitted. There is a reduction in the interference in noise. There is due to reduced bandwidth. As the bandwidth increase, the amount of noise added to the signal will increase. Now, the disadvantages of SSB-SC. The main drawback of SSB-SC modulation is that it is expensive and highly complex to implement, because SSB transmitter and receiver need to have an excellent frequency stability. A slight change in frequency will harm will hamper the quality of the transmitted and received signal. That's why SSB is not generally used in broadcasting applications. Now, the applications of SSB-SC. SSB transmission is used in application where the power saving and low bandwidth requirements are important. The applications area are land and air mobile communication, telemetry, military communication, navigation, etc. And many of these applications are point to point. So this is the end of this lecture. Here we have discussed about single sideband suppressed carrier signal generation and detection process. Also we have discussed the advantages, disadvantages and application of SSB-SC system. This was 11th lecture of the lecture series of basics of communication engineering. In the next lecture, I would like to discuss about vestigial sideband transmission VSB AM system and types of AM transmitter and receiver. Till then, thanks for listening this lecture. Thank you.